Chapter 1, Some Basic Concepts of Chemistry. Chemistry is the science of molecules and their transformations. It is the science not so much of the 100 elements but of the infinite variety of molecules that may be built from them. Roald Hoffman. Science can be viewed as a continuing human effort to systematize knowledge for describing and understanding nature. You have learned in your previous classes that we come across diverse substances present in nature and change in them in daily life. Curd formation from milk, formation of vinegar from sugarcane juice on keeping for prolonged time, and rusting of iron are some of the examples of change which we come across many times. For the sake of convenience, science is subdivided into various disciplines: chemistry, physics, biology, and geology, etc. The branch of science that studies the preparation, properties, structure, and reaction of material substances called chemistry. Development of chemistry. Chemistry, as we understand it today, is not a very old discipline. Chemistry was not studied for its own sake, rather, it came up as a result of research for two interesting things. First, philosopher stone, that is called Paradise, which would convert all baser metals, example iron and copper, into gold. Second, elixir of life, which would grant immortality. People in ancient India already had the knowledge of many scientific phenomena much before the advent of modern science. They applied that knowledge in various walks of life. Chemistry developed mainly in the form of alchemy and electrochemistry during 1300 to 1600 CE. Modern chemistry took shape in the 18th century Europe after a few centuries of alchemical traditions, while traditions which were introduced in Europe by the Arabs. Other cultures, especially the Chinese and the Indian, had their own alchemical traditions. These included much knowledge of chemical processes and techniques. In ancient India, chemistry was called Rasayan Shastra, Rastantra, Raskriya, or Rasvidya. It includes metallurgy, medicine, manufacture of cosmetic, glass, dyes, etc. Systematic excavation at Mohenjo-daro in Sindh and Harappa in Punjab prove that the story of development of chemistry in India is very old. Archaeological findings show that baked bricks were used in construction work. It shows the mass production of pottery, which can be regarded as the earliest chemical process in which materials were mixed, molded, and subjected to heat by using fire to achieve desirable qualities. Remains of glazed pottery have been found in Mohenjo-daro. Gypsum cement has been used in the construction work. It contains lime, sand, and traces of CaCO3. Harappans made faience, a sort of glass which was used in ornaments. They melted and forged a variety of objects from metals such as lead, silver, gold, and copper. They improved the hardness of copper for making artifacts by using tin and arsenic. A number of glass objects were found in Maski in South India 1000 to 900 BCE and Hastinapur and Taxila in North India 1000 to 200 BCE. Glass and glassware colored by addition of coloring agents like metal oxide. Copper metallurgy in India dates back to the beginner of Chalcolithic cultures in the subcontinent. There are much archaeological evidence to support the view that technologies for extraction of copper and iron were developed indigenously. According to Rig Veda, tanning of leather and dyeing of cotton were practiced during 1000 to 400 BCE. The golden gloss of the black polished ware of northern India could not be replicated and is still a chemical mystery. These were these wares indicate the mastery with which clean temperatures could be controlled. Kautilya's Arthashastra described the production of salt from sea. A vast number of statements and material described in the ancient Vedic literature can be shown to agree with modern scientific finding. Copper utensils, iron, gold, silver ornaments, and terracotta discs and painted grey pottery have been found in many archaeological sites in North India. Sushrut Samhita explained the importance of alkalis. The Charak Samhita mentioned ancient Indians who knew how to prepare sulfuric acid, nitric acid, and oxides of copper, tin, and zinc, the sulfates of copper, zinc, and iron, and the carbonates of lead and iron. Rasopanishda described the preparation of gunpowder mixture. Tamil texts also describe the preparation of fireworks using sulfur charcoal, saltpeter, that is potassium nitrate, mercury, camphor, etc. Nagarjuna was a great Indian scientist. He was a he was a reputed chemist, an alchemist, and a metallurgist. His work, Ras Ratnakar, deals with the formulation of mercury compounds. He has also discussed method for the extraction of metals like gold, silver, tin, and copper. A book, Ras Arnava, appeared around 800 CE. It discuss the uses of various furnaces, ovens, and crucible for different purposes. It described methods by which metals could be identified by flame color. Chakrapani discovered mercury sulfide. The credit for inventing soap also goes to him. He used mustard oil and some alkalis as ingredients for making soap. Indians began making soap in the 18th century CE. Oil of Iranda and seeds of mahua plant and calcium carbonate were used for making soap. The painting found on the walls of Ajanta and Ellora, which look fresh even after ages, testify to a high level of science achieved in ancient India. Varamahir Brihad Samhita is a sort of encyclopedia which was composed in the 6th century CE. It informs about the preparation of glutinous material to be applied on walls and roofs of house and temples. It was prepared entirely from extracts of various plants, fruits, seeds, and barks, which were concentrated by boiling and then treated with various resins. It will be interesting to test such materials scientifically and assess them for use. A number of classical texts like Arthaveda 1000 BCE mention some dye, sunflower, or piment, cochineal, and like some other substance having tinting property were Kamplisika, Patanga, and Jatuka. Vadamahir's Brihat Samhita gives reference to perfume and cosmetic. Recipe for hair dyeing were made from plants like indigo and minerals like iron power, black iron or steel, and acidic extract of sour rice gruel. Gandhayukli describe recipe for making scent, mouth perfume, bath powders, incense, and talcum powder. Talcum powder. Paper was known to India in the 17th century as account of Chinese traveler. Eystein describe excavation at Takshila indicate that ink was used in India from the 4th century. Colors of ink were made from chalk, lead, and red lead, and minimum. It seems that the process of fermentation was well known to Indians. Vedas and Kautilya's Arthashastra mention about many types of liquids. Charak Samhita also mention ingredients such as barks of plant, stem, flowers, leaves, woods, cereals, fruit, and sugarcane for making asavas. The concept that matter is ultimately made of indivisible building blocks appeared in India a few centuries BCE as a part of philosophical speculation. Acharya Kanda, born in 600 BCE, originally known by the name Kashyap, was the first proponent of the atomic theory. He formulated the theory of very small indivisible particles, which he named Parmanu, comparable to atoms. He authored the text Vaiseshikha Sutras. According to him, all substance are aggregated from form of smaller units called atoms, Parmanu, which are eternal, indestructible, spherical, suprasensible, and in motion in the original state. He explained that this indivisible entity cannot be sensed through any human organ. Kanda added that there are varieties of atoms that are as different as the different classes of substance. He said these Parmanu could form pairs or triplets among other combinations, and unseen force cause interaction between them. He conceptualized this theory around to 2500 years before John Dalton, 1766 to 1844. Chadak Samhita is the oldest Ayurvedic epic of India. It describes the treatment of diseases. The concept of reduction of particle size of metal is clearly discussed in Chadak Samhita. Extreme reduction of particle size is termed as nanotechnology. Charak Samhita described the use of bhasma of metals in the treatment of elements. Nowadays, it has been proved that proved that bhasma have nanoparticles of metals. After the decline of alchemy, electrochemistry reached a steady state, but it too declined due to the introduction and practice of Western medical system in the 20th century. During this period of stagnation, pharmaceutical industry based on Ayurveda continues to exist, but it too declined gradually. It took about 100 to 150 years for Indians to learn and adopt a new technique. During this time, product poured in as a result, indigenous traditional techniques gradually declined. Modern science appeared in Indian scene in the latter part of the 19th century. By the mid 19th century, European scientists started coming to India and modern chemistry started growing. From the above discussion, you have learned that chemistry deals with the composition, structure, properties, and interaction of matter, and is of much use to human beings in daily life. These aspects can be best described and understood in terms of basic constituent of matter, that are atoms and molecules. That is why chemistry is also called the science of atoms and molecules. Can we see, weigh, and perceive these entities, atoms and molecules? Is it possible to count the number of atoms and molecules in a given mass of matter and have a quantitative relationship between the mass and the number of these particles? Uh, we we will get the answer of some of these question in this unit. We will further describe how physical properties of matter can be quantitatively described using numerical value with suitable units. 1.1 Importance of chemistry. Chemistry plays a central role in science and is often intertwined with other branches of science. Principles of chemistry are applicable in diverse areas such as weather patterns, functioning of brain, and operation of a computer production in chemical industries, manufacturing fertilizers, alkalis, acids, salts, dyes, polymers, drugs, soap, detergents, metal alloys, etc., including new material. Chemistry contribute in a big way to the national economy. It also plays an important role in meeting human needs for food, healthcare product, and other material aimed at improving the quality of life. This is exemplified by the large scale production of a variety of fertilizers, improved variety of pesticides and insecticides, Chemistry provides methods for the isolation of life-saving drugs from natural source and makes possible synthesis of such drugs. Some of these drugs are cisplatin and Taxol, which are effective in cancer therapy. The drug is AZT, azithromycin, is used for the helping AIDS patient. And, chemistry contributes to a large extent in the development and growth of a nation. With a better understanding of chemical principle, it has now become possible to design and synthesize new material having specific magnetic, electric, and optical properties. This has led to the production of superconducting ceramics, conducting polymers, optical fibers, etc. Chemistry has helped in establishing industries which manufacture utility goods like acid, alkalis, dyes, polymers and metals, etc. These industries contribute in a big way to the economy of a nation and generate employment. In recent years, chemistry has helped in dealing with some of the pressing aspects of environmental degradation with a fair degree of success. Safer alternatives to environmentally hazardous refrigerants like CFCs, chlorofluorocarbon, responsible for the ozone depletion in the stratosphere, have been successfully synthesized. However, many big environmental problems continue to be matters of grave concern to the chemist. One such problem is the management of the greenhouse gases like methane, carbon dioxide, etc. Understanding of biochemical process, use of enzymes for large scale production of chemicals, and synthesis of new exotic material are some of the intellectual challenges for the future generation of chemists. A developing country like India needs talented and creative chemists for accepting such challenges. To be a good chemist and to accept such challenges, one needs to understand the basic concepts of chemistry, which begin with the concept of matter. Let us start with the nature of matter. 1.2 Nature of matter. You are already familiar with the term matter from your earlier classes. Anything which has mass and occupies space is called matter. Everything around us, for example, book, pen, pencil, water, air, all living beings, etc., are composed of matter. You know that they have mass and they occupy space. Let us recall the characteristic of the states of matter which you learned in your previous classes. 1.2.1 States of matter. You are aware that matter can exist in three physical states. Physical state is solid, liquid, and gas. The constituent particles of matter in these states can be represented as shown in figure 1.1. Particles are held very close to each other in solids in an orderly fashion, and there is not much freedom of movement. In liquids, the particles are close to each other, but they can move around. However, in gases, the particles are far apart as compared to those parent in solid or liquid states, and their movement is easy and fast. Because of such arrangement of particles, different states of matter exhibit the following characteristic. First, solid have definite volume and definite shape. Second, liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. One figure 1.1 Arrangement of particles in solid, liquid, and gaseous state. Third, gases have neither definite volume or nor definite shape. They completely occupied by the space in the container in which they are placed. These three states of matter are interconvertible by changing the conditions of temperature and pressure. सॉलिड को हीट दिए तो लिक्विड बना, लिक्विड को हीट दिए तो गैस बना, गैस को कूल करेंगे तो लिक्विड हुआ और लिक्विड को कूल करेंगे तो सॉलिड हुआ. On heating, A solid usually challenges to a liquid, and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling liquefies to the liquid, and the liquid on further accepting freezes to the solid. 1.2.2 Classification of matter. In class 11th, chapter 2, you have learned that at the macroscopic or bulk level, matter can be classified as mixture or pure substance. This can be further subdivided as shown in figure 1.2. Will all constituent particles of the substance are same in chemical nature, it is said to be a pure substance. A chemical mixture contains many types of particles. A mixture contains particles of two or more pure substance which may be present in any ratio. Hence, their composition is variable. Pure substance forming a mixture are called its component. Many of the substance present around you are mixtures. For example, sugar solution in water, air, tea, etc. All mixtures. A mixture may be sorry. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components completely mixed with each other. This means particles of components of the mixture are uniformly distributed throughout the bulk of the mixture, and its composition is uniform throughout. Sugar solution and air are the example of homogeneous mixtures. In contrast to this, in a heterogeneous mixture, the composition is not uniform throughout, and sometimes different components are visible. For example, mixtures of salt and sugar, grains and pulses, along with some dirt, often stone pieces, are heterogeneous mixture. You can think of many more examples of mixtures which you come across in the daily life. It is worthwhile to mention here that the components of a mixture can be separated by using physical methods, such as simple hand picking, filtration, crystallization, distillation, etc. Pure substance have characteristic different from mixtures. Constituent particles of pure substance have fixed composition. Copper, silver, gold, water, and glucose are some example of pure substance. Glucose contains carbon, hydrogen, and oxygen in a fixed ratio, and its particles are of same composition. Hence, like all other pure substance, glucose has a fixed composition. Also, its constituent carbon, hydrogen, and oxygen cannot be separated by simple physical method. Pure substance can be further classified into elements and compounds. Particles of an element consist of only one type of atoms. These particles may exist as atoms or molecules. You may be familiar with atoms and molecules from the previous classes. However, you will be studying about them in detail in Unit 2. Sodium, copper, silver, hydrogen, oxygen. It is are some example of elements. There, all atoms are of one type. However, the atoms of different elements are different in nature. Some elements such as sodium or copper contain atom as their constituent particles, whereas in some others the constituent particles are molecules which are formed by two or more atoms. For example, hydrogen, nitrogen, and oxygen gases consist of molecules in which two atoms combine to give their mm, in which two atoms combine to give their respective molecules. This is illustrated in figure 1.3. uh, यहाँ पे figure 1.3, a representation of atoms and molecules. When two or more atoms of different elements combine together in a definite ratio, the molecules of a compound is obtained. Moreover, the constituent of a compound cannot be separated into simpler substance by physical methods. They can be separated by a chemical methods. Example of some compounds are water, ammonia, carbon dioxide, sugar, etc. The molecules of water and carbon dioxide are represented in figure 1.4. Note that a water molecule comprises two hydrogen atoms and one oxygen atoms. Similarly, a molecule of carbon dioxide contains two oxygen atoms combined with one carbon atom. Thus, the atoms of different elements are present in a compound in a fixed and definite ratio, and this ratio is characteristic of a particular compound. Also, the properties of a compound are different from those composed of a compound are also, the properties of a compound are different from those of its constituent elements. For example, hydrogen and oxygen are gases, whereas the compound formed by their combination, that is, water, is a liquid. It is interesting to note that hydrogen burns with a pop sound, and oxygen is a supporter of combustion, but water is used as a fire extinguisher. 1.3 Properties of matter and their measurement. 1.3.1 Physical and chemical properties. Every substance has unique or characteristic properties. These properties can be classified into two categories: physical properties, such as color, order, melting point, boiling point, density, etc., and chemical properties like composition, combustibility, reactivity with acid and bases, etc. Physical properties can be measured or observed without changing the identity or the composition of the substance. The measurement of the observation of chemical properties requires a chemical change to occur. Measurement of physical properties does not require occurrence of a chemical change. The example of chemical properties are characteristic reaction of different substance. These include acidity or basicity, combustibility, etc. Chemists Chemists describe, interpret, and predict the behavior of substance on the basis of knowledge of their physical and chemical properties, which are determined by careful measurement and experimentation. In the following section, we will learn about the measurement of physical properties. 1.3.2 Measurement of physical properties. Quantitative measurement of properties is required for scientific investigation. Many properties of matter, such as length, area, volume, etc., are quantitative in nature. Any quantitative observation or measurement is represented by a number followed by units in which it is measured. For example, length of a room can be represented as 6 meter. Here 6 is the number and m denotes meter, the units in which the length is measured. Earlier two different systems of the measurement, that is the English system and the metric system, were being used in the different parts of the world. The metric system, which originated in France in late 18th century, was more convenient as it was based on the decimal system. Late need of a common standard system was felt by the scientific community. Such a system was established in 1960 and is discussed in below. Detail below. 1.3.3 The International System of Units SI. The International System of Units in French, Les Système International D Units, abbreviated as SI, was established by the 11th General Conference on Weight and Measures (CGPM) from Conference General des Poids et Measures. The CGPM is an intergovernmental treaty organization created by a diplomatic treaty known as the Meter Convention, which was signed in Paris in 1875. The size system has even base units, and they are listed in Table 1.1. These unit pertain to the several fundamental scientific quantities. The other physical quantities, such as speed, volume, density, that is etc., can be derived from these quantities. Uh, maintaining the national standards of measurement. The system of units, including unit definitions, keeps on changing with time. Whenever the accuracy of measurement of a particular unit was enhanced substantially by adopting new by new principles, members nation of meter treaty signed in 1875 agreed to change the former definition of that unit. Each modern industrialized country, including India, has a National Metallurgic Institute (NMI), which maintains standards of measurement. This responsibility has been given to the National Physical Laboratory (NPL), New Delhi. This laboratory establishes experiment to realize the base units and derive units of measurement and maintains national standards of measurement. These standards are periodically intercompared with standards mentioned at other national metallurgy institute in the world, as well as those established at the International Bureau of Standard in Paris. Table 1.1, Base physical quantities and their units. Base physical quantities, symbol for quantity, name of SI unit, and symbol for SI unit. Length L, meter M, mass M, kilogram kg, time T, second S, electric current I, ampere A, thermodynamic temperature T, Kelvin K, amount of substance N, mole, मोल एक, नेम ऑफ ऐसा यूनिट में है MOLE एंड सिंबल फॉर ऐसा यूनिट में है MOL. Luminous intensity IV, candela and CD. The definition of the SI base units are given in the table 1.2. The SI system allows the use of prefixes to indicate the multiples or sub-multiples of a unit. These prefix are listed in table 1.3. Let us now quickly go through some of the quantities which you will be often using in this book. Table 1.2, definition of SI base unit. Unit of length, meter. The meter symbol m is the SI unit of length. It is defined by taking the fixed numerical value of the speed of light in vacuum C2V, C2V 2997 uh, 299792458 when expressed in the unit ms inverse, where the second is defined in terms of the cesium frequency delta BCS. Unit of mass, kilogram. The kilogram symbol kg is the SI unit of mass. It is defined by taking the fixed numerical value of